Okay. So in this problem, we need to find the reactions again. The way this problem is presented, this material, you can see it's kind of cast and tapered. It looks like kind of a concrete. So this is a solid, connected kind of asymmetric T shape. So this connection at B is going to be what? It's going to be a fixed connection. All right? You can see out here at C, it's free, so it's able to cantilever and flex any way it likes. So you get down here to A, you can see this symbol. It probably indicates that that's also a fixed connection. So I'm going to draw my free body diagram. I'm going to draw a line for the beam portion and then another line for the column portion. And now I'm going to make some assumptions about what's happening here at A. Just like the previous problem, I'm going to assume that my unknown AY is acting up, positive. AX is to the right. And since I told you previously I like right-hand rule, I'll go ahead and assume that my moment reaction there is also, in my sign convention, positive. So I'm just assuming these are all positive for my sign convention. Let's see, I should probably put some dimensions. This column is 10 feet high. The cantilevered part is 12. And this little back cantilever is 3. And how am I going to handle the distributed load? Well, if you look at it, it's rectangular, so that's not too bad. So we know the area of this rectangle is just the base times the height. So the base is 15, and the height is 0.6. So that's 9. Is that right? And it's going to act what? In the center of this. Well, the center of this at a distance of 15 is going to be 7.5. So I've got a 9 kip force, 7.5 feet from both sides. And then what's happening out here on the end? There's another force to the right, and that's 5 kips. I think that's everything I need. I think about our determinacy problems. I've drawn one free body, so how many equations do I get? 3. And how many unknowns do I have? 3 equals 3. Pretty easy. Now I think this is one that really tells you that when you sum moments, you should probably pick a good spot. If I decide to sum moments right there, what would happen? You could do it. It'd be one equation in 1, 2, 3 unknowns. That's a terrible way to start your equation. One equation, 3 unknowns. In fact, I discourage you from trying to solve these problems by writing simultaneous equations and solving them that way. I suggest you find a way that you can write one equation and one unknown and then move forward. Now you could say, well, how about this point? Well, at least AY passes through, but you still got the moment at A and the moment due to AX. So the point that I think is the best one is to start right here at A. First of all, the two forces are concurrent at A, so they don't create moment. So you only have one unknown, the actual moment at A. So again, I'm going to sum moments using right-hand rule. And in this case, I'm going to sum moments at A, and we're going to say it's in equilibrium. So there's our first statement. So let's actually do that. So summing moments about A, the reaction moment, which I called M sub A, with this sign convention, right-hand rule, what kind of moment is that? Positive or negative? Positive. So I'll just write MA. The concentrated equivalent force here, what kind of moment does it create about A? Positive or negative? Negative. You can see as it pushes down, straight down this line, it's going to try to rotate clockwise, which is negative. So I'll say negative 9 kips. And what's the distance between A and that line of action? It's this little distance here, which is what? 4.5. Yeah, it'd be 7.5 minus 3. It should be 4.5. Now the second moment created about A is by this 5 kip force here that's horizontal. What kind of moment is that? Positive or negative? negative again, right? It's going to go clockwise. So that'll be 5 kips is the force. And what's the distance from the line of action of 5 to A? It's the height of the system, which is 10 feet. So we can solve for the moment at A. It looks like it's going to be positive, and it's going to be, I don't know what it's going to be. Somebody help me with that. Something less than 100. 90.5? So that's going to be kip feet moment. And again, the positive value means I assume the right direction. Does that make sense to you? All these forces on this thing are trying to rotate this structure about A which way? Clockwise or counterclockwise? No. The forces are trying to rotate about A clockwise, so the reaction should be opposite. Don't forget to just check those things. Okay, now what do? Some force is X, some force is Y. Or does it matter? It doesn't seem like it matters. So I'll just, because I did X last time, I'll do Y this time. There's no pattern for that. So I'm going to sum forces in the Y direction. There's my equilibrium statement. I'm going to assume up is positive. So let's collect the sum. So I'm looking at my reaction AY. It is up, so it's positive in my equation. What else is happening in the Y direction? This 9 equivalent, concentrated equivalent is 9, and it is down. That is not a hard equation to solve. Looks like AY is equal to 9 kips. And then last, we'll sum forces in the X direction. Make sure it's in equilibrium. So there's our statement. And what do we have in the X direction? So I assumed AY was acting to the right. That matches my sign convention. So I have AX. What else is in the X direction? Our 5. Is it positive or negative? Positive. So that's easy to solve too. AX is negative 5 kips. Now at this point, whether it's positive or negative doesn't really matter, except if I ask you as an end result, show me the final position of all your reactions. Okay? Then you would come over here with AX and you would draw it backwards. Not on the free body diagram, just as a final result. Later in the course, whether it's positive or negative will mean something to us. Right now, we're not too worried about it. Any other questions about that one? Probably also wish that one was on Mastering Engineering, huh?